So can you see the slides? Okay. So yeah, so today I'm going to talk about some data-driven approaches to study molecules in materials. So the chemical informatics really deals with data to understand the structure property relationships of the molecules in materials. And so basically the goal here is, given the structure of the molecules or the materials, one would like to predict the properties of those molecules. And here the properties could be growth state energies or even excited state energies. And in addition to this mapping from the structure to the properties, chemical informatics also allows the inverse mapping going from the property to the structures. In other words, one can define the property one wants to achieve first, and then the algorithm comes up with the structures that would have such a property. So really, this informatics allows the bidirectional mapping between the structures and properties based on the chemical data. And here is an example, so a typical example of informatics being applied to an application such as in organic light emitting diode field. In OLED, the basic design principle is to have a molecule with the right triplet energy and also small singlet triplet gaps, because in a so-called thermally activated delayed fluorescence mechanism, the rate of fluorescence is really inversely proportional to the single triplet gaps. And these days, quantum chemistry methods allow reasonably accurate predictions of single triplet gaps for conventional molecules. However, if the number of candidate molecules is a larger scale, such as of the order of millions of molecules, then one cannot afford to do quantum chemistry calculations for all those candidate molecules. And that's where this machine learning method may come in, so that one could have a simplified model that could predict the properties of molecules, such as single triplet gaps here. And so in this example, Asper Guzik and coworkers used some kind of fingerprint as a descriptor of the molecules, and they built up a model that allows us to calculate the single triplet gaps. And then they built a large library of 1.6 million OLED candidate molecules, basically combining various donors and expressing bridges in a combinatorial manner. And then they applied this machine learning model for such a library that has been generated. And then they selected about 1,000 of them that might be interesting and they might be promising. And then they obtained some sort of expert voting, then finally chose about 5 to 10 candidates that are synthesized for the validations. And then they obtained several blue OLED molecules with reasonably high quantum efficiency. And so then so this entire thing was possible because they had this model that allows the prediction of single triplet gaps based on the data. And so the simple concepts that are used in chemical science can be captured in this quick example. And if I summarize them again, then there are basically three sort of categories where the usages of machine learning can be applied in chemical science, namely property predictions and exploring chemical space and synthesizability. Basically, if you have the data and a way of representing the data, then one can perform a property prediction model. And that's an example that I just showed you for the prediction of single triplet gaps for OLED applications. And the second aspect is exploring the chemical space. Basically, chemical space is a space of valid molecules. And the goal is to find the molecules with the target properties. And because the chemical space is almost literally infinite, finding a chemical with the target property in this vast space is very difficult, and one needs a very efficient method. Currently, we all use mostly chemical intuitions by the expert knowledge. But here, the goal is really to use the data to explore the chemical space so that the machine gives some sort of hidden knowledge about the chemical space. And then the third category is the synthesizability predictions, because as a computational chemist, we design molecules and materials computationally, but we also know that many of them are indeed discarded in the laboratory because they are not synthesized. And so it would be good to have a model that could predict the synthesizability of those compounds ahead of experiments. So these are the sort of three usages of machine learning in chemical science. But today, I'll be focusing on the first and third aspects, property predictions and synthesizability aspects due to the time limit. Okay, so the property prediction first. So like I said, if you have a data and a way of representing the data, then one can set up a simple regression model or sometimes sophisticated ones. And then that would allow us to predict the property of the unknown compound. Once the data is given, the accuracy of the prediction is affected greatly by how you represent the data. And so far, feature engineering has been pretty popular, meaning that you basically use simple attributes of the properties that you're interested in as an input of the model. And this is also sometimes called the physics-derived models. For example, for catalysis applications where calculating the absorption energies is quite important, people have used dB in the center, electronegativity, and higher moments of the density, and etc., as an input of the model that can calculate the absorption energies for simple adsorbates on various metal alloy surfaces. And also we've worked on this field, and our motivation here was to have a model where the descriptors do not require additional computational burden. And so we use the electronegativity and dB in the width computed from the mean field model, so that we have the analytical expression so that the descriptors can be computed easily without any post-processings. Now, feature-based predictions are pretty promising, but could be quite cumbersome, because if you are interested in a different property, then you need to come up with a different set of descriptors again. And that requires expert knowledge. And so it would be good to have a sort of a way of representing the molecules in a more general way. It's similar to a situation where in electronic structure calculations, we use the Hamiltonian of the molecule, regardless of the properties that you're interested in, either singular triplet gaps, homolumo gaps, or polarizabilities. You always use the structure of the molecules, right? So similarly, people are trying to encode the molecules with their structures that go into the model. And one popular approach is the graph-based method. In graph-based method, you represent the atoms as nodes and then chemical bonds as edges. And it is important to incorporate the chemical environment properly. In other words, you know that B is surrounded by E, F, G, and A is also surrounded by B, C, D, and then you have second neighbors. And this kind of information can be transferred by a mathematical operation called convolutions. And these sort of convolutional graph-based methods have showed promising results for electronic properties for molecules, and also the electronic properties for the crystal structures as well. And this graph-based method, we have used it to make a prediction for the triplet energies of for OLED applications. And we've used here 30,000 DFT data for triplet energies, and we were able to obtain about 0.08 electron volt meter, which is reasonably okay for prediction purposes. And so this was possible by the use of graph convolutions. Now, since you have now a tool to calculate the triplet energies of a molecule without DFT calculations, you can generate a massive library of molecules using either generative models or some random mutations of the already known materials. And then you can use this machine learning model to filter out those ones that belong to your target sort of triplet energy ranges. And these are some of the examples where we have generated random mutations of the existing molecules and then apply this machine learning model to filter out those that are within the emissions. Another example of graph-based methods applied to catalysis applications. And here the Ulysses group constructed a graph-based method that allowed the calculation of the binding energies for various metal surfaces. And they obtained about 0.13 electron volt meter. The accuracy was quite promising, but one sort of a bottleneck, which is the case for all graph-based method, is the fact that in order to use graphs, you need the three-dimensional structure of the molecules. And to obtain that, you need to perform some kind of geometry optimizations, for example, using DFT. So the motivation for us to have a model that can predict the binding energies without geometry optimizations. So to that end, instead of encoding the structure of the adsorbate bound structures, we removed gas adsorbates and then labeled those active sites with fake atoms and then encoded the slab geometries only. Then that way you can remove the step for geometry optimizations when the adsorbate is bound. And here's the benchmark results. The prediction accuracy for CO binding and H binding for about 400 binding energy data for various metal alloys. Our work shows pretty comparable accuracy compared to previous results, sometimes better, sometimes slightly worse. But the key difference was the fact that our method does not require geometry relaxations. So we thought that this could be a way of practically representing the catalyst surfaces for catalysis applications. In fact, the key motivation of working on this sort of representations was to study this kind of experimental system. This is the system studied by the Jung group at UCLA, and they made nickel binary straight nanowires, and then they dealloyed the nickels, and they are left with the platinums. But along the course of dealloying, the straight nanowire becomes very much amorphous, and their morphology has ups and downs, and hence they name the structure as jagged platinum nanowires. We all know that it's quite well known that even for the same platinum surfaces, depending on the fast, that's 110, 100, or 111, they have different coordination numbers. And therefore, they have very different activity experimentally measured. And so you can imagine that this platinum nanowire would have all sorts of coordination numbers. And so, so in order to understand this system, one needs to consider every single active site of the materials and take some kind of statistical averaging to really understand the experimental results. But we also understand that DFT optimization of this jagged platinum nanowire for every single active site is intractable. So that's why we need the method that would allow us to compute the binding energies without geometry relaxations. And that's why we worked on this. And since we now have the method, we applied it to these jagged platinum nanowires. And this is the results compared for experiments and theory. And you can see a reasonable agreement between theory and experiments, namely the current density as a function of the potential. Now, with this agreement, we were finally able to understand why jagged platinum nanowire shows such a high enhanced activity compared to conventional platinum nanowires. Hydrogen evolution reactions consist of two steps. First step is the adsorption of the proton from the solution to the platinum surface. And then hydrogen atoms adsorbed on the platinum surface are coupled and and hydrogen molecule are produced. And we found that because of these amorphous like structures, certain platinum sites are pretty good at adsorptions, while others are pretty good at hydrogen-hydrogen couplings. So we realized that hydrogens are adsorbed in one site, favorable for the adsorptions, and then diffuses to the sites where the couplings are more favorable. And then they get, and then hydrogen. And so this is basically a bifunctional mechanism where two different morphologies give you the synergies such that the overall activity is enhanced by a factor compared to the conventional mechanism. And I want to emphasize that the understanding was possible because you had a method that allows us to compute the binding energies without DFT relaxations. Now I want to talk about synthesizability next, because as I mentioned, many of the molecules and materials that we computational design oftentimes end up being discarded because they are not synthesized. And so it would be good to have a classification model that tells us whether a compound is synthesizable or not. But this is different from the conventional classification task because in conventional classification, you have the positive and negative data. And when the model is trained, when the unknown data comes in, the model predicts whether it's positive or negative. But in our case of synthesizability, if the material has been synthesized, we know that it's positive data. But if the material has not been synthesized, hypothetical data, then that does not necessarily mean that it's not synthesizable, because later on it may be still synthesized. So basically, we only have the positive data, and then the rest of the data are unlabeled, basically. So we need to do some kind of iterative learning. So we've done that for Materials Project database, inorganic crystal database, which is about 50,000 synthesized positive data, and then remaining 80,000 data are unlabeled. They are basically obtained by the substitution of the already synthesized materials, these hypothetical data. And our model after training showed about 87% accuracy, which is reasonable. And to validate the model, we intentionally excluded the data that have been synthesized between year 2015 and year 2020. And then tested if the model can still predict the synthesizability of those materials that have been intentionally excluded. We still get about 86 to 87% accuracy. One thing that we found pretty interesting was the fact that the thermodynamics and then the synthesizability scores are not directly related, including us, because there's no quantitative metric that estimates the synthesizability of the inorganic crystals. People often use the thermodynamics as a measure of the synthesizability of the crude because there's nothing else. However, we find that thermodynamic, as you can see here, many of the structures that are sort of thermodynamically stable still have very low synthesizability scores, meaning that they might not be synthesizable. So synthesizability basically is related to thermodynamics, but is beyond. There is something more than that, something beyond that. And as a further validation, here we have sort of in this 80,000 hypothetical data, we selected the top 100 materials with highest synthesizability scores, and looked up the literature whether any of them have been indeed synthesized and reported. We find that 71 out of 100 have been already synthesized and reported. So these would be the case where the materials have been synthesized but have not been deposited in the database. So that database considers them as hypothetical. But our model predicts them to be synthesizable 71% of the time. And this is my last subject, which is the synthesizability for organic compounds instead of inorganic crystals. For organic molecules, rather than the synthesizability, a more relevant question would be the synthesis pathways. And that has the special name of retrosynthesis. And there are many retrosynthesis models in literature. But our idea was the following: if this is your target molecule, which you want to synthesize, the goal is to predict the reactants that would produce this product. And in that prediction, basically what you're trying to do is you're trying to identify the reaction center where to cut the bond. So for example, in this bond. And the next task is how you cap those bonds that are cut. And those combinations, reaction center and the capping sort of functional groups need to be determined simultaneously. And so that was the key idea of our approach. And then at the end of the day, you have sort of a conditional probability of where to cut and what kind of template you need to apply. And at the end of the day, you'll have rank 1 reactants, rank 2 reactions, all the way down to rank n possible reactants. And top 5 accuracy, for example, refers to the fact that the correct answer would be within the top rank 5 predictions. So our model has about 85 to 92% top 5 accuracy. And here's a sort of practical application of our approach for a molecule. In this case, a drug candidate molecule. And this is a target molecule. And this molecule has been synthesized in 7 steps starting from this reactant. And we took this example from this literature. And our model has reasonable predictions. So the first step, we predicted with rank 1, and rank 1, rank 1, rank 1, and rank 7, rank 1, and rank 2. So most of the steps are predicted reasonably well by our model. And this is another example for, in this case, OLED organic light emitting diode candidate molecule. And this is the candidate molecule, and this is the starting molecule that are in the literature. And our model predicts this correct path with rank 6 or rank 2 predictions. So it's not a perfect prediction, but it's a reasonable. And also I want to emphasize that although so top 1 results that our model predicts are different from the actual sort of reaction pathways. Reaction pathways are not unique, and then these reaction pathways might also be working as well, and that they may even give some novel intuitions for organic chemists. And that would be our hope. Okay, so today I talked about sort of a couple of usages of machine learning for studying the molecules in materials, and because this concept of the theme of the workshop is the light matter interaction, I try to connect with some applications related to OLED applications. All right. So with that, I would like to acknowledge my students, Juhan, Kunho, Jidon, Songwon, and Shuan.